Let's take a quick look at how to take a sample of some data and be able to turn it very quickly into an estimating tool for values and probabilities associated with the underlying population from which the sample was drawn. So we want to take a sample like this one we have here. What you'll typically want to do is come up with a good estimator of values associated with your population. So let's start by taking just the basic descriptive statistics of our values. I'm going to plug that in here and take all my values associated with the matrix. I want to turn on the labels. I'll take an output range. Let's put our values maybe right here in column C. Come up with the summary statistics and go ahead and run those. So here's our basic descriptive statistics. Now I could have just done a couple of Excel functions maybe to get the mean or the variance, something like that, but typically when I'm given a sample of data, the first thing I do is I run descriptive statistics on it. Now in terms of the maximum likelihood estimators for the population of a normal distribution, if I assume the data is fairly normal, this data doesn't look too far off, so I'm going to go ahead and color my mean red, because the mean itself, x bar, is the maximum likelihood estimator for the mean of the underlying population. But the variance of the sample is not a good estimator for the overall variance and standard deviation of the population as a whole. So for that we need to take the deviation squared, because the formula for the MLE for the normal distribution is the sum of the deviations squared divided by the sample size. So I need to take, if you will, each of these minus the mean and lock that in. And I need to square that value, so I should have put that in brackets in the first place. Let's do that and square that value. That's the deviation squared for the first value, and I can take the rest of the values as I work my way down. I took too many, obviously. Let's take some of those out. Okay, so here's my deviation squared. I can sum those values. Right here, I can't do type today. There's the sum of those values, so that is my sum of the deviation squared, and then I want to divide that by the sample size, which is D15 in this case. So 369.09 is the MLE estimator for my variance. So I could take my standard deviation, so this is my sigma hat there, so basically my standard deviation hat would be the square root of that as I go through. So that is the square root that I would use to build my calculator as I see my way forward. Now I took a lot of steps here to do the deviation squared. I was basically applying the formula for the MLE estimator of the variance of the normal distribution population from a sample. I could have taken a shortcut. Having run the Excel descriptive statistics, I could have started from their variance. So if I could have taken this 410, and if you think about what is the formula for the sample variance of a sample, it's the sum of the deviation squared divided by n minus 1, so 1 less. So this was already divided by n minus 1, so if I were to multiply this by n minus 1, in this case that would be 9, I would get the value like I did before, and then I divide that by 10, I get the MLE value. So it's possible, if you've run the descriptive statistics in Excel, to get the MLE value for sigma hat without having to go through the work of calculating the deviation squared, largely because the tool already did it for you in order to come up with this standard deviation. So whichever way you do it, you end up with that number. 369.09 is the variance of the population, where the variance of the sample was slightly larger as I went through. So now I understand what the MLE estimates for both my variance and my mean are. I can come up with a kind of calculator for my process. So suppose what I want to know is the percentile of something, maybe the 95th percentile of something as I go through. And I've assumed my data is normal. That's the way I'm working with it. So if I do a norms dist, norms inverse rather, with a probability, and I put the probability in, then z 1.644854, typically written as 1.645, is the z that I'm looking for. So I can look at the percentile of my data to find out what that is. So basically I'm looking for, okay, so if I simply take my mean, can I add to that my z factor times my standard deviation, I get 417. So that's the 95th percentile of my data. If I wanted the 90th percentile, I could plug that in now. If I want the 50th percentile, I can plug that in. But that gives me a percentile calculator as I go through. The other way I tend to do this calculation is if I know an x, I want to calculate the z, I want to be able to calculate the probability of that. So maybe my x of 400 might be a z of my x value minus my mean. Okay, I should have put that in parentheses, obviously. Divided that by my sigma calculation. Okay, and then my probability is simply the norms distribution of that probability. Gives me this a 76%. The probability of being x 400 or less is 76% as I go through. So again, if I want to measure it against any other value going through, 410 or 405, whatever value I want to plug in. So these two values here become, if you will, the inputs to my calculator. I'm going to mark those as blue like I often do on input parameters. And the output parameters are, are these two parameters coming through. So I'm going to mark those in red because they're the answers that I want. And there I have it. It's a very simple calculator for calculating both the MLE estimates of the mean and the variance of my population given a small sample, and then the two calculators for doing calculations against it as I go through. So having these kinds of spreadsheets around to quickly calculate these kinds of things against basic distributions is a big plus.